Welcome to the full video lecture on inference for two samples. The content in this video can be found in the Lock 5 textbook, Chapter 6, Sections 3 and 4. These are the learning objectives that we're going to be covering. For each of these learning objectives, we'll be looking at the difference between two proportions and the difference between two means. First, we'll identify the appropriate distribution, the normal, binomial, or t distribution. Second, we'll construct confidence intervals. And third, we'll conduct hypothesis tests. Here's our lecture organization. Again, we'll start with two proportions, walking through these three learning objectives. And then we'll look at two means, again, walking through the same three learning objectives. Let's start with the difference between two proportions, identifying the appropriate distribution. A couple of weeks ago, you used StatKey to construct bootstrap and randomization distributions for the difference in two proportions. Here we have one of those randomization dot plots. This example uses a relatively small sample size, so we can see that there are large gaps between each of the possible proportional differences here. This example uses the same proportions, but larger data set. Here, the distribution is approximately normal. The rules that we'll be applying to determine whether or not our sampling distribution can be approximated by a normal distribution is similar to what we looked at last week with the rule of sample proportions. Here, if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 in both groups, we use the z distribution. So the only difference between what you saw in the last lesson and in this lesson is now this must be true for both groups. If n times p is less than 10 or n times 1 minus p is less than 10 in either group, we use a binomial distribution. When using the z distribution, Minitab Express refers to this as the normal approximation method. When using a binomial distribution, Minitab Express refers to this as Fisher's exact method. This might be a good time to stop and take a quick break. What we just covered is in the Lock 5 textbook, Chapter 6, Section 3-D. If you feel comfortable with this material, you might want to go right to the Wiley Plus assignments to work through a few problems. When we come back, we'll move on to confidence intervals. In terms of formulas, I'm just going to show you the formulas that are associated with the normal approximation method. This is the general form of a confidence interval that you've been working with for a few weeks now. We can apply this for the difference in two proportions as well. Now, our sample statistic is the difference in the two sample proportions. So the proportion of group 1 minus the proportion of group 2. Our multiplier under the normal approximation method will be a z multiplier. And our standard error is now computed as the square root of p hat 1 times 1 minus p hat 1 divided by n1 plus p hat 2 times 1 minus p hat 2 divided by n2. We put these together and we have our formula for the confidence interval for the difference between two proportions. I'm going to walk through one example by hand, and then I'll walk through that same example using Minitab Express. These data were collected, I believe, in the spring 2017 semester from a representative sample of World Campus students. They were asked, what is your biological sex, female or male, and do you currently own wearable technology, for example, an iWatch or a Fitbit? Yes or no. We want to construct a 95% confidence interval for the difference in the proportions of females and males in the population who own wearable technology. First, we need to check the assumption to make sure that we can use the normal approximation method. For confidence interval, in order to use the normal approximation method, n times p and n times 1 minus p in both groups must be greater than or equal to 10. In other words, there needs to be at least 10 successes and at least 10 failures in each group. For the females, there were 89 people who said yes, which means there were 194 who said no. In the males, there were 53 who said yes, which means that there were 164 who said no. These values are all at least 10, so we can use the normal approximation method. We then plug these values into our formula. Here, we have the difference in sample proportions, plus or minus our z multiplier. You might recall from previous weeks that for a 95% confidence interval, 1.960 is the z multiplier, times the standard error. Now I'm going to take you to Minitab Express to show you how this confidence interval could also be constructed there. We'll go to Statistics, to Sample Inference, Proportions. We're going to be entering in summarized data. Sample 1 we'll say is our females, because we were computing the difference in females minus males. There were 89 females that said yes, they own wearable technology, out of 283. Sample 2 then will be our males. There were 53 out of 217. We'll check our options. The default is a 95% confidence interval. The default test method is to estimate the proportions separately. When we're conducting a hypothesis test, we're going to leave this test method to the default, estimate the proportions separately. We'll click OK. And here we have our 95% confidence interval for the difference. To interpret this, I would say that I am 95% confident that if we would take the population proportion for females minus the population proportion for males, that difference would fall between negative 0.008454 and positive 0.148950. This is another good breaking point. You might want to go to the textbook or to Wiley Plus now to review the questions related to the Lock 5 textbook, Chapter 6, Section 3-CI. When you come back, we'll move on to hypothesis testing for the difference in two proportions. When conducting a hypothesis test for the difference in two proportions, we're going to be using the 5-step hypothesis testing procedure again. Steps 1 and 2 may be slightly different from last week, but steps 3, 4, and 5 are still going to be the same. We'll start by looking at step 1. If n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, in both groups, use the z distribution. Minitab Express will call this the normal approximation method. If this assumption is not met, you can use the same steps in Minitab Express, but you would look at the Fisher's exact test, p-value, instead of the normal approximation method, z-test statistic, and p-value. When we're doing this by hand, I'm just going to be showing you the normal approximation method. These are the different hypotheses that you can see for a difference in two proportions test. Note that here we see the null hypothesis is P1 minus P2 equals 0. This is equivalent to saying P1 equals P2. Step 2 is to calculate the test statistic. This formula for the test statistic follows the same general form that you saw earlier. It's the difference in sample statistics minus the null parameter, which for a difference in two proportions test is always going to be 0, divided by the standard error. The standard error here can be a little bit trickier to calculate because the standard error assumes that the null hypothesis is true. In other words, it assumes that the two proportions are equal. So the proportion that's going into this standard error here, p hat, is actually a pooled estimate of p. This is a way of averaging the two proportions while taking into account the different sample sizes. Before you can compute a test statistic, you need to compute the standard error, and before you compute the standard error, you need to compute the pooled estimate of p. Steps 3, 4, and 5 are going to be the same as what we've worked with previously. For determining the p-value in step 3, you're going to construct a normal distribution, and you're going to find the area that is more extreme than the z-test statistic that you computed in step 2 in the direction of the alternative hypothesis from step 1. Step 4, make a decision. If your p-value is less than or equal to the alpha level, you reject the null hypothesis. If your p-value is greater than the alpha level, you fail to reject the null hypothesis. And then in step 5, you state a real-world conclusion. So go back to the original scenario or the original research question and answer that question. Let's look at an example. We're going to be using the same data set that we saw earlier when we constructed our confidence interval. Now we want to know, are the proportions of females and males who own wearable technology different? Step 1, write hypotheses and check assumptions. We'll start by checking assumptions, which we actually saw earlier. Again, we're going to check to make sure that there are at least 10 successes and at least 10 failures in both groups. This assumption is met, so we can use the normal approximation method. Next, we write our hypotheses. The research question is asking if there is a difference between females and males. It doesn't give us a direction. This is going to be a two-tailed test. Our null hypothesis is that the proportion of females equals the proportion of males. The alternative hypothesis is that the proportion of females does not equal the proportion of males. Step 2, compute the test statistic. Computing the test statistic here can get a little bit lengthy, so I'm actually going to start a fresh page. Here we have our formula for the test statistic for two independent proportions. We have the difference in the sample minus 0, and that 0 is coming from the null hypothesis. Recall, P1 equals P2 is equivalent to saying P1 minus P2 equals 0. That's where this 0 is coming from. The standard error formula we have here, which includes P hat, the pooled estimate of P. We're going to start by computing the pooled estimate of P. Note that P hat 1 times N1 is really the number of successes. So if we look at our fractions here, this turns into 89 plus 53 in the numerator, and then the denominator 283 plus 217. So it's taking both samples and combining them, and it's almost like saying if we ignored biological sex, what would the overall sample proportion be? In this case, 0.284. And to double check your work on this, the pooled estimate of P should always be somewhere between the two group sample proportions. Now we can compute the standard error. The two formulas that you see here are identical. I'm going to be using the second formula here. I think it's a little bit easier to follow. When we do out the math, we get a standard error of 0.0407. Now we can go back to our formula for the z-test statistic. The difference in our two sample proportions divided by the standard error gives us a z-test statistic of 1.712. Step 3 is to determine the p-value. We'll go to Minitab Express now to construct a z-distribution to find the area that is more extreme than z equals 1.712 in the direction of the alternative hypothesis. We have a two-tailed hypothesis here, so we're going to be looking at the left and right sides of this z-distribution. We'll go to Statistics, Probability Distribution, Distribution Plot, to display our probability. We have a z-distribution, which is the default. Our z-test statistic is a specified x value. We have a two-tailed test, so the p-value is going to be evenly split between the left and the right tails. The x value, which is actually our z-test statistic here, is 1.712. Our p-value is the total area in the tails. So we'll have to add together the left tail and the right tail, which will give us a total area, a total p-value of 0.0868. Now that we have our p-value, we can move on to step 4. Make a decision. Our p-value is greater than our standard alpha level of 0.05, so we will fail to reject the null hypothesis. And step 5, state a real-world conclusion. We failed to reject the null hypothesis, so there is not evidence that the proportions of females and males who own wearable technology differ in the population. In other words, our results are not statistically significant. Now I want to go back to Minitab Express to show you how steps 2 and 3 can be completed there. We'll go to Statistics, to Sample Inference, Proportions. We have Summarized Data. Sample 1 is our females. They were 89 out of 283 who owned wearable technology. Sample 2 will be our males. There were 53 out of 217 who owned wearable technology. Under options, the default is a two-tailed alternative hypothesis, which is what we have here. For the test method, we will need to change this. For hypothesis testing, we use the pooled estimate of the proportion. This is because we want to construct that sampling distribution given that the null hypothesis is true, and the null hypothesis says that the two population proportions are equal. We'll have to scroll down and we'll get our z-test statistic and p-value. Recall in step 1, we checked to make sure that we had at least 10 successes and at least 10 failures in both groups, so we're using the normal approximation methods, z-test statistic, and p-value. If that assumption was not met, then we would just use the Fisher's exact method. Our z-test statistic again is 1.73, and our p-value is 0.0843. So that would go in steps 2 and 3 of the 5-step hypothesis testing procedure. This is another good stopping point. What we just covered is in the Lock 5 textbook, Chapter 6, Section 3.ht. When you come back, we'll start again with the difference in two means. We just covered sampling distributions, confidence intervals, and hypothesis testing for the difference in two proportions. Now we're going to move on to cover the same learning objectives for the difference in two means. Let's begin by looking at when to use the z and t distributions. This diagram should look familiar to you from last week. The difference is that now we're looking at both populations. So we need to start by asking ourselves, are the populations both normally distributed? If yes, then we want to know if the population standard deviations are both known. If yes, then you could use a z distribution. Most of the time, the population standard deviations will not be known and the t distribution will be used. If we don't know if the populations are both normally distributed, we would then ask, are both sample sizes at least 30? If yes, then we would use the t distribution. If no, then we would use the bootstrapping and randomization methods that you learned a few weeks ago. What we're focusing on in this lesson, though, is the t distribution method. This is also known as an independent means t-test. This is a good time to stop to take a quick break to go to Wiley Plus to answer some of those questions from Chapter 6, Section 4-D. When you come back, we'll look at confidence intervals. We're going to be constructing confidence intervals for the difference in two means using the t distribution method. Here's our general form of a confidence interval that you've seen several times before. Now, our sample statistic is the difference in the two sample means. X bar 1 minus X bar 2. Our multiplier is going to be a t multiplier. Recall that the t distribution varies depending on degrees of freedom. Here, we're going to estimate the degrees of freedom by taking the smaller sample size and subtracting 1. Note that this is an estimate of the degrees of freedom. The formula that Minitab Express uses is much more complicated. But when we're doing these by hand, this is the method that you're going to use to make it a little bit easier for yourself. And the standard error is going to be equal to the square root of the variance of group 1 over the sample size of group 1 plus the variance of group 2 divided by the sample size of group 2. Pay special attention to these formulas. S squared is the variance, not the standard deviation. This is the standard deviation squared. We put these values together and we get our formula for the confidence interval for two independent means. Let's walk through one example. First, I'll show you how to construct a confidence interval by hand, and then we'll go to Minitab Express to do the same example there. We have data from a representative sample of World Campus students concerning their biological sex and height in inches. In this table here, we have descriptive statistics. We want to construct a 95% confidence interval for the difference in the mean weights of males and females. We can start by computing the difference in the samples. So the mean of males minus the mean of females equals 6.3587. Next, we can find our t multiplier. We'll construct a t distribution with 208 degrees of freedom. We're estimating these degrees of freedom by taking the smaller sample size and subtracting 1. Let's go to Minitab Express now to construct that t distribution to find our multipliers. I'm going to construct a probability distribution plot to display a probability. This is going to be a t distribution with 208 degrees of freedom. We want to find the t-scores that separate the middle 95% from the outer 5% of this t-distribution. We have equal tails, and 0.05 is split equally between those two tails because we want to construct a 95% confidence interval. Here, our t multiplier is 1.971. Next, we can compute the standard error. This is just a matter of taking the standard deviations and sample sizes from our descriptive statistics and plugging them into our formula. We get a standard error of 0.3067. Now we can put all of these values together. Our sample statistic plus or minus our t multiplier times our standard error. We have a margin of error of 0.6045 and a 95% confidence interval of 5.754 to 6.963. To interpret this confidence interval, I would say that I am 95% confident that if we would take the mean weight of males minus the mean weight of females in the population, that difference in means would be between 5.754 inches and 6.963 inches. Now, I want to take you back to Minitab Express to show you how this confidence interval could be computed there. I'm going to show you this in two different ways. First, we'll use the summary statistics that we have. We'll go to Statistics, to Sample Inference, T. We'll enter in our summarized data. Sample 1 will be our males. The sample size was 209 with a mean of 70.3529 and a standard deviation of 3.2274. Sample 2 is our females, a sample size of 265, with a mean of 63.9942 and standard deviation of 3.4229. We'll check the options. We're going to be using the default settings here, a 95% confidence level, and you want to make sure that this box for assuming equal variances is not checked. We'll click OK, and here we have our 95% confidence interval for the difference. Again, 5.7560 and 6.9614. Next, I want to show you how you could construct this confidence interval if you had a data set open in Minitab Express. Here I have my data set open. I'm going to follow the same procedure to start. Statistics, two-sample inference, T. But now, I'm going to say that both samples are in one column because I have one column with all of the heights in it. Samples is our quantitative variable, here heights. Sample IDs are the biological sexes. We'll double check the options, but we're going to keep the default settings here because we want a 95% confidence interval. We click OK. One difference you'll see here is that in Minitab Express, by default, it goes in alphabetical order. So here it's taking females minus males, which we can see at the top that it's calling mu sub 1 the female means and mu sub 2 the males means. So our confidence interval here is the same numbers, but in a different order, a negative, because we're taking the mean of females minus the mean of males. So now it's negative 6.9614 to negative 5.7561. To interpret this confidence interval, I could say that I am 95% confident that if I would take the mean height of females in the population minus the mean height of males in the population, that difference in means would be between negative 6.9614 and negative 5.7561. This is a good place to stop and take a break. You can go back to the online notes or textbook or to Wiley Plus to review the Lock 5 section 6.4-CI. When you come back, we'll continue with hypothesis testing. This is the last topic that we're going to cover, conducting a hypothesis test for the difference in two means. Steps 3, 4, and 5 are still going to be the same as they've always been. Steps 1 and 2 might be a little bit different from what you've seen in the past. Step 1, we'll check assumptions. We're going to look at that flow chart from before. The majority of the time you're going to be using the t distribution, because most of the time you either know that the populations are approximately normal or you have sample sizes that are at least 30. Then we write our hypotheses. Here the null hypothesis is written as mu sub 1 equals mu sub 2, but again recall that this is the same as saying mu sub 1 minus mu sub 2 equals 0. Step 2 will calculate the test statistic. For means, the standard error formula is the same for hypothesis testing and confidence intervals. So unlike with proportions when you had to worry about whether or not you had to estimate the proportions together separately, you don't have to worry about that with means. The standard error formula is the same. Sometimes you'll also see this written with a minus 0 in the numerator, because recall the null hypothesis is that mu sub 1 minus mu sub 2 equals 0. A lot of times though that 0 just gets dropped out and you see the test statistic formula written like this. For step 3 then, you would determine the p-value by constructing a t-distribution. Degrees of freedom for that t-distribution are still going to be estimated as the smallest sample size minus 1. Step 4, you compare your p-value to your alpha level to determine if you should reject or fail to reject the null hypothesis. And step 5, state a real-world conclusion. Let's look at an example now. Again, we'll look at this first by hand using the formulas, and then I'll take you to Minitab Express. We're going to be using the same data set that we just worked with the confidence interval, but now we have a different research question. We want to know, is there evidence that the heights of males and females are different in the population? Step 1, write hypotheses and check assumptions. The population shape is unknown, but our sample sizes are both at least 30, so we can use the t-distribution. This is a two-tailed test because our research question just asks if the means are different in the population. It doesn't give us a specific direction. Step 2, compute the test statistic. Here we have our formula again. It's the difference in sample means divided by the standard error. We plug the numbers from our descriptive statistics into this formula. Again, be careful with that standard error formula because it contains the variance, not the standard deviation. So it's S squared. We end up with a difference in sample means, again, of 6.3587 and a standard error of 0.3067 and a test statistic of 20.733. This is a huge test statistic, which we'll see in a moment when we go to Minitab Express to find our p-value. Before we can find our p-value, we need to compute our degrees of freedom, which is the smaller sample size minus 1. We're now going to construct a t-distribution with 208 degrees of freedom to find the area more extreme than 20.733. I'll go to Statistics, Probability Distribution, Distribution Plot. To display a probability, we have a t-distribution with 208 degrees of freedom. We now have a t-test statistic, which is a specified x value of 20.733, and this is a two-tailed test, so we have equal tails. On this distribution, we see a p-value of 0. Theoretically, a p-value can never equal 0. There's always at least a very, very slight chance that a type 1 error was committed. So what we would say in this case is p is less than 0.001. In other words, the p-value is very small. It is less than 0.001. With this very small p-value then, in step 4, we would reject the null hypothesis. Step 5, we rejected the null hypothesis, so there is evidence that the heights of males and females are different in the population. Now I'm going to take you to Minitab Express, where I had this data set open to show you how you could work through this there. We'll go to Statistics, to Sample Inference, T. Our samples is our quantitative response variable of height, and then sample IDs are our two groups, biological sex. Under options, we can confirm that we do have a two-tailed alternative hypothesis. Click OK. We'll scroll down past the confidence interval, and here we have our hypothesis test. We have a t-test statistic. It's negative this time because, again, Minitab Express does this in alphabetical order, so it's doing females minus males, which is the opposite of what we did when we did this by hand. But t-test statistic of negative 20.73. The degrees of freedom that Minitab Express computes is different from what we computed by hand. When we did this by hand, we took the smaller sample size minus 1. Minitab Express is using a much more complicated algorithm for computing these degrees of freedom. Our p-value, though, is exactly the same. P is less than 0.0001. Now we have covered all three learning objectives for both the difference in two proportions and the difference in two means. There's one last thing that I want to share with you. This is in your online notes. It highlights all the formulas that you've seen in this lesson. For the confidence interval and the test statistic formulas, remember that they're following those same general forms that you've been working with for weeks now. For the confidence interval, it's always going to be the sample statistic plus or minus a multiplier times a standard error. For the test statistic, it's always going to be sample statistic minus the null parameter divided by standard error. So when you're looking at these formulas and when you're looking at these in relation to the ones that you saw in the last lesson, try not to get overwhelmed. Remember that they're all following that same general form. This concludes the video lecture. As always, if you have any questions following this video or as you're working through any of the materials in this lesson, please post them to the discussion boards on Canvas or attend one of the live tutoring sessions with Penn State Learning.